I'd now like to welcome Dr. Rob Murdoch from another valued partner of ours, NIWA, to provide an update on the latest climate data. Welcome, Dr. Rob.
Thanks very much, Vicky, and kia ora tātou. It's a pleasure for us to be able to come along and give you a little presentation on climate change. Thank you, everyone. What I'm going to do today is I will give you a little bit of an update about what's happening to our climate system right now, and then I'm going to focus in, as it says on the slide, on impacts of extremes, because in fact, it's the extremes and the intensification of the extremes as a consequence of climate change, which are the things that we really should be thinking about when it comes to climate adaptation. And I'm going to actually finish up with looking at Cyclone Gabriel, because that's a good example of the extremes that we can continue to expect. And some of the intensity of these storms is increasing because of the climate change. And I'll talk about some of the science tools that we're developing to enable us to start to make some of the decisions around how we're going to adapt to these extreme events. So that's the talk. This is a global model output of what we can expect around global temperatures if we continue to proceed towards a 2-degree increase in global average temperature above pre-industrial levels by 2050. And I think it's fair to say at the moment that the science community is pretty much convinced that because we've been unable to reduce emissions in any way globally, that the likelihood of getting to 2 degrees, I know we've been trying to get to 1.5 degrees, but the reality is we're likely to exceed 2 degrees at this stage. And if the planet does, of course, not every part of the globe will be the average temperature, and the blue area there shows where, in fact, we can expect to see somewhere around about a 2-degree increase in global temperatures, and you'll see that New Zealand actually sits in that space. So our temperature is only expected to increase by around 2 degrees or less. The issue is that parts of the Northern Hemisphere are going to be substantially above that. In fact, Northern Europe could expect to be up to 8 to 10 degrees above their current average temperatures. And unfortunately, these models are proving to be correct. And if we look at what's happening around the globe, these are things that I downloaded last week. So in the US, we're seeing record high temperatures now in the southern states. They were getting temperatures above 46 degrees in some of their states last week, up to over 115 degrees Fahrenheit and well above their average. Europe is warming faster, twice as fast as any other continent on the planet, which is consistent with what the model predictions actually say. And probably of more concern is the fact that nearly all of the oceans on the globe are now the warmest they've ever been recorded. And this picture in the middle is showing you those areas where, in fact, temperatures in some cases are up to 5 degrees warmer than average. And that's important because the oceans have actually taken up around 90% of all the additional heat due to the extra greenhouse gases we've put on into the atmosphere over the last 150 years or so. And of course, that heat's being trapped in the oceans. The top 3 meters of the ocean hold as much heat as the entire atmosphere. So this heat is now on the planet, and it's going to take some time for the oceans to cool, but that has a massive impact on our climate. And the Southwest Pacific is being impacted by these changes in the climate system. If you look at and actually in the Southwest Pacific, most of these numbers are actually coming from Australia and New Zealand, given we're the 2 largest countries in this part of the world. But you'll see that in 2021, the blue areas are floods and the orange areas are storms. There were about 57 reported cases. There are 1,000 deaths, mainly due to storms, 14.3 million people impacted, mainly due to storms, but equal costs in terms of the storms and the floods, and into the many billions. And around about 2006, I think it was, I was actually asked by the NIWA board to give a presentation on climate change adaptation. And this was my opening slide. So what is happening in New Zealand and what do we need to do? And in fact, if you go back to 2006, a lot of the messaging then around the fact that we needed to start acting on climate change because the climate was changing haven't changed actually, and really most of the world has not done a lot around climate change adaptation. So the messaging is still the same, and at about the same time, a man by the name of Nicholas Stern, he was contracted, an economist, was contracted by the UK government to do an analysis of the costs of climate change, and he was looking at both mitigation and adaptation, and he produced this 800-page report. And today it is still the most comprehensive analysis that's been done. He was slammed back then as being a scaremonger in terms of his predictions of how the climate was going to change, and he was told that he was being far too excessive in terms of estimating the costs. It turns out a reanalysis of his report is that he underestimated on both counts. And so if we're going to build resilience, we should be starting to act now, because the costs of doing things now is certainly going to be nowhere near the costs if we don't later. And in New Zealand, there's plenty of evidence that our climate's changing. We know that our temperatures here have increased by just over 1 degree since 1909. NIWA is recording near record high temperatures almost every month somewhere in New Zealand. We've been undertaking surveys of the volume of glacier ice in the Southern Alps since 1978, and our surveys are showing that we've lost 30%. They've lost 30% of their ice since that time. We know that our sea level has increased by around 20 centimetres since 1900, and of course we're starting to see a greater frequency of things like marine heat waves, fires, and extreme floods. And our measurements dating back to the 90s off the Otago coast is showing that our oceans around New Zealand are acidifying, and in fact the global oceans are about 30% more acidic than they were pre-industrial times. So our climate is changing, and it has already changed. And there's a lot of regional modelling to look at how we might expect to see New Zealand change in the future based on various emission scenarios. These are just just to give you some idea of the information that we're generating. And this is slightly out of date now, and NIWA has actually been contracted by MFE to produce the next lot of definitive projections about how New Zealand's climate might change under various emission scenarios. But if we continue the way we are in terms of our emissions, and these are showing what we might expect to see in terms of various climate variables out to around about 2090. So the first graph on the left there, the map on the left, the dark red areas show where the number of days above 26 degrees each year is expected to go from its current number, which is around about 30, up to 90. So we can see a tripling in the number of hot days, and certainly in the northern part of the country, but things are going to get much hotter. The middle one shows what will happen with rainfall. And to some extent, New Zealand's a little bit blessed here, because it shows that overall we can expect to have more rainfall. And there are many countries around the world that are already in deficit. They don't have enough water to meet their daily needs. And the number of countries in that predicament is expected to increase. The problem we have is that where the areas of rainfall are going to be isn't quite necessarily where we'd want them to be. So the dark green and blue areas show where the amount of rainfall is going to be above average compared to today. And it's the other problem is that most of it's going to fall on extreme events. It's going to fall in winter, and we're going to have less rainfall in summer. And of course, that has implications for things like drought. And the picture on the right, the brown areas show where what is currently a 1 in 20 year drought is expected to become a 1 in 5 year drought or less. So we're not only going to have more water in the winter, but we're actually going to have more droughts in the summer. So that's just some idea about what we can expect in the longer term if things continue the way they are. Probably the most worrying one, though, is this one, and that's sea level rise. So over the last 100 years, we've had a 20 centimetre rise in sea level, and this is for Wellington. And over the next 20 years, we're expecting a 30 centimetre rise in sea level. So the rate of sea level rise is actually increasing. And what this means in Wellington, the problem in Wellington is it's exacerbated because some of that increase in sea level is actually due to the fact that we're subsiding. So If you add those two things together, you can expect about a 30 centimetre increase between now and 2040. And what that means is that every time we have a big storm, a 1 in a century year storm causing storm surge, which is the big issue, is going to become an annual event. And 2040 isn't very far away. But the premise of this talk is that actually the slow gradual change is actually easier to adapt to. The issue really is it's the extremes in weather and our climate associated with climate change, because those extremes are intensifying. So if we're going, and that's primarily driven by the variability in our climate, and that's what I want to talk about now. But if we can adapt to that variability in our climate, then we're going to be in a much better position to adapt to climate change. But we have to think of extremes, because it's the extremes that actually do most of the damage. So this is just an example of the climate variability. So if you look at what's happened to New Zealand's average temperature over the last 100 years, you can see the blue line there, which is the average overall, and you can see the 1 degree increase in temperature. But you can see behind that, the red line is actually what happened on an annual basis. And there's huge variability where we go way above the average temperature or way below. And that's what I'm meaning by climate variability. Our climate from year to year varies significantly. And why? It's mainly driven by the El Nino, La Nina cycles that we have. So if you look at the picture on the left, under an El Nino situation, we end up with a situation in the middle Pacific where most of the warm water is up against the Americas. And this is due to the fact that the trade winds wane in an El Nino, and the water tends to flow across to the east. And of course, all of the upwelling along the Americas ceases. So all that cold water coming up from depth doesn't happen. And what happens in our part of the world is that we tend to see a colder water than average. La Nina is the complete opposite. You get a strengthening of the trade winds, you get a build-up of the warm water on the eastern side, and you get all that upwelling and colder water on the Americas. And this has a massive impact on all of the globe's weather patterns, not just ours. And a good measure of the level of La Nina or El Nino is actually the difference can be measured by the difference in pressure between Tahiti and Darwin. And that's because the pressure systems, the atmospheric pressure systems shift. And you can see here a really strong correlation between what's known as the Southern Oscillation Index, which is based on that pressure difference, and temperature, which is the top graph. And this is actually the temperature of the Americas. And you can see there that when the pressure difference is greatest, you get a decrease in the average temperature and vice versa. And that's the difference between El Nino and La Nina. So the warmer period for the Americas, of course, is an El Nino, and you can see that that's a time where the difference in pressure is lowest. So it's a really good predictor of what we're of El Nino, La Nina, and we can use this to help us with our seasonal forecasting around this. And I talked about the pressure differences. So if you take the average pressure during an El Nino event, this is a sort of picture that you get, and the little arrows show the winds. So in an El Nino, you get effectively the high pressure belt sitting across Australia and northern New Zealand. That's the pink areas there. And you see from the winds that actually the winds over New Zealand during El Nino are predominantly from the west. So we get a whole bunch of westerly winds, and they're dragging the warm, dry air off the Australian continent onto New Zealand. La Nina is the complete opposite. The high pressure bands and the high pressure systems tend to move across the southern part of New Zealand. And we've seen that over the past year. And what that does is that it sets up wind patterns where it's dragging winds from air from the tropics, which is moisture laden, down to New Zealand. And by the time it gets to New Zealand, it's taken on an easterly flow, and that's why it hits the eastern side of New Zealand. And of course, that's been what we've seen over the last year. And this is just a picture of the difference in sea surface temperature between January 30th and June the 4th this year. And you can see how that equatorial Pacific area has changed incredibly rapidly. So we've gone from this situation, which is an El Nino, to very much a La Nina, through to an El Nino situation where you can see that building up of hot water, warmer water against the Americas, up to 5 degrees more than average. And we can see that in the Southern Oscillation Index. If you have a look, that's what it's currently telling us. So in the month of May, you can see that the little pink bar at the far right, we've suddenly gone from what's been predominantly La Nina over the last 3 years to an El Nino situation. And based on the size of that bar, the predictions are that we're going to have, at this stage, a strong El Nino event this coming summer. And what does that mean for New Zealand? Well, if you look at the right-hand graph, this is what tends to happen in New Zealand. So with all those westerly winds and the warm, dry air coming from Australia, we tend to have very dry conditions. This is the summer rainfall. And you can see it's going to hit Northland and the upper part of the North Island the most, but also those firn winds coming off the Alps dries out the eastern side of the South Island as well. And of course, we see the opposite with La Nina, all of that wet, moist air coming down from the north and hitting the country from the northeast. Northland, Gisborne areas, Hawke's Bay, all heavily hit with rain. And of course, we see the Southland with droughts, and that's exactly what we've been seeing over the last 2 to 3 years. So this coming summer, chances are we're going to end up with drought conditions in parts of the North Island, particularly Northland. But I now want to just focus in on the extremes and what sort of tools we might need if we're going to think about how we adapt to extreme events. And when I'm talking about extreme events, I'm talking about droughts, which is a climate extreme, if you like. But the others are weather extremes, which are the fires that may result from those droughts, but also floods and damaging winds and waves. They're the key elements. And of course, we've been seeing a lot of these over the last 12 months. One of the most important things we need to understand is the risk. And if we're talking about hazard risk, there are 2 elements that we need to be able to measure. One of them is the probability or the chance of that hazard event occurring. And the other one is what are the impacts of that event if it does occur? What are the losses? What are the costs? And this is just an example of the sort of information that we need to collect. So this is the graph shows a rainfall gauge graph in the middle of Auckland, and we've plotted on it the extreme rainfall event in January that we had. And you can see there that this particular rain gauge recorded 280 millimetres over a 24-hour period. And that equated, based on historic data, to 1 in a 100-year flood event. And the pictures, of course, on the other side show that you need to get out and actually look at what particular infrastructure, what land use, what infrastructure is actually exposed and what the damages are, so you can understand the impacts. And if you know that information, you can then do a proper risk analysis. The issue around climate change, and the reason we also need to look at what future projections are telling us, is that that's going to shift that graph. And what's actually happening is that a 1 in a 100-year flood, of course, is now coming more frequently. And over the last we've been funded through a number of providers have got together and being funded through MB to produce flood risk models and tools so that we can use this information, because floods are actually now one of our biggest costs in terms of planning into the future. And it's looking at 3 types of floods. It's looking at flash floods, which are the sort of floods that we had in Auckland, shown in the left-hand picture there. River floods, such as the situation with Cyclone Gabriel. And then looking at storm surge, which is actually the impacts of storms on our coastal environment, which of course is influenced by sea level rise as well. So those three types of floods. And it's a complex process. You need a whole bunch of information around the digital elevation models. You need to understand the river networks. You need to understand the infrastructure associated with those rivers. You also need a whole bunch of information around rainfall. You need to understand and have catchment information so that when you do model rainfall events, that you can actually model what's happening in the rivers, and you have to combine all that information. And if it's coastal, you need to include tides. So it's not an insignificant exercise to do this. And then when you come to produce a national flood map, you need to generate your storms with a model. You need to be able to generate the floods. You need to model those floods, and of course you combined all of the geodetic information as well, and hopefully at the other end you get out a national flood map. At the moment, New Zealand doesn't do this well. It's very inconsistent. We don't have a lot of the data you need. You need really good LiDAR data, for example. And so we're attempting to try and get something that's done consistently in the same way across the whole nation, so we can actually use this in decision making. And this is an example of some of the modelling that can be done. This is Westport showing actually the July reenactment of the July 2021 flood. You can see the influence of the tides, and you can see which parts of the town get flooded, particularly on high tides for this particular event. And of course, this was a 1 in 100 year event, although they've had 2 or 3 of them in the last 5 years. We also did some really interesting work, and it's quite a complex exercise to work out how much of this particular flood was actually due to the increased intensity that we have that's been created through climate change over the last 100 years. And it's quite pioneering work, but they managed to show that 6% of the severity of the July 21 flood was actually due to climate change. So that's a large proportion of the $54 million insurance claims. And then we take that information, and there we have a model called RiskScape, and this is a model, multi-hazard model that has been developed by NIWA and GNS, and we now have EQC as a partner as well to further develop this model. So you take the flood inundation maps, you combine it with all your built environment, your land use maps, and then we can apply, we've done a huge amount of work looking at the vulnerability of various assets and lands, and you combine all that information, and out the other end you get a risk analysis. And we're currently also working on how we can look at various climate change scenarios and various adaptive strategies, and what the cost benefit analysis is of the different options. So we're hopeful that this will be available to stakeholders over the next couple of years with all of these elements included. And this is just an example of RiskScape. It's an open source software now, the actual engine for RiskScape, and we're now collecting all of the data together. And you can see this is a picture of Westport under a 1 in a 100 year flood event, and we can actually identify the red dots, individual households that are going to be impacted. And I just want to just demonstrate how we can use this information with Cyclone Gabriel. Not long after the flood, we sent a lot of scientists up to look at the actual extent of the flood, understanding and you have to do it pretty much straight away to get an idea of what has actually been impacted by the flood. We then did LiDAR surveys using helicopter to work out where a lot of the sediment had gone, how the rivers had changed shape. The picture at the bottom there with the red and the blue shows the area where there's been sediment built up, and the red areas show where it's been carved away. And we had really good forecasting information. NIWA's high resolution forecasting enabled us to rerun the storm again to look at what was happening. The purple areas in that picture on the right show where we had predictions of rain, 24-hour rainfall that were up to 0.5 metre. And they actually predict really well relative to the rain gauges that were there, which are the dots. And we were also able to simulate the floods again with our models. And the graph on the bottom shows what we predicted with our models versus what was actually measured in the rivers. And you can see we've got a really strong correlation. So we were able to rerun these models to reenact the floods and to find out what actually happened. And in fact, to work out why the flood banks broke where they did and what the impact of that was. But if you add all of this information too into RiskScape, then we can generate these sorts of pictures. This is just one example. And this is showing the recovery costs for individual properties. The blue areas are showing where it's in the order of 0 to 100,000, if you like, in recovery cost. But if you get up to the red areas, then you're talking about potentially 300 to 9 million in terms of recovery costs. But this information is really important. And in fact, all of this information is being used by DPMC in terms of looking at what the recovery from this event should look like in terms of where we rebuild, where we don't, and what areas get red stickered and which ones don't. So in terms of adaptation, this sort of information is essential. And this is actually an old picture, but it actually shows some of the work we did with Riskscape to look at what happens if sea level increases by 50 centimetres, and that could be as early as 2050. And then what happens when you get a storm surge on top of about 1 metre. And just to put that into perspective, we saw a storm surge of close to 1 metre along Coromandel and parts of Northland with Cyclone Gabriel. So this isn't an extraordinary event that we're talking about. But if you do that, you can see there for the green areas, our estimates of the sorts of infrastructure that would be impacted and what the potential costs were, how many buildings are impacted and what sort of residential populations would also be impacted. And it's quite significant, but we need to have this sort of risk information if you're going to plan accordingly. So just to finish up, I think our messages here are that the climate's changing. And our extremes are intensifying. And this is largely driven by the variability in our climate. And that really, if we're going to truly adapt to climate change, we need to start thinking about how we can adapt to that variability and in particular the extremes. And we are developing the tools to enable us to do that through this high resolution hazard risk information and identifying what infrastructure and what the costs are going to be. And I think when it comes to building resilience, we really do need to think about, have we got the right information and data? Is the risk analysis sound? And use that information then to plan and prioritise and make the appropriate investment decisions around our climate risks. So Vicky, that's it from me. Thank you. I hope that's been informative.